So, how exactly do you teach a machine to make a really smart decision, especially when the information's a bit fuzzy and the stakes are high? That's what we're going to break down today. And we'll do it by walking through a simple but very telling story. Okay, let's meet Lisa. She is out in the forest, minding her own business, when she spots a paw print. And this thing is massive. We're talking 14 centimeters. Instantly, she's got a choice to make. Is it safe to keep picking mushrooms, or is it time to head home? Fast. This one question, believe it or not, is a perfect window into how machines learn to think. All right, so the very first piece of the puzzle is the evidence itself. In the world of machine learning, this is what we call the likelihood. And if you just look at the size of that paw print, I mean, it's pretty much screaming wolf. So based only on that single clue, the case seems closed. It's gotta be a wolf. But wait a second, we don't make decisions in a total vacuum, right? And neither should our machines. This is where a really core idea comes into play, the prior probability. You can think of it as your starting assumption. It's all the general knowledge you have in your head before you even see the specific evidence. And this is a huge piece of context for Lisa. She knows her local area. She knows that for every one wolf out there, there are probably 100 free-roaming dogs. So her prior belief, her gut feeling to start with, is that any animal track she finds is overwhelmingly likely to belong to a dog. So how do we mash these two things together? How do we combine what we already believed with this new, specific evidence? Well, that's the magic of something called Bayes' rule. It gives us what we call the posterior probability, which is just a fancy way of saying it's our new, updated, and much more informed belief. It's the math of how to properly change your mind. And check this out. This chart shows exactly what happens. On the left, you can see the likelihood, based on that huge paw print, is yelling wolf. But then we combine it with that really strong prior belief, the fact that dogs are 100 times more common. And boom, the final answer, the posterior probability, completely flips. The math now says there's about a 90% chance it's a dog, even with that giant print. Now, what's really cool about this is that it hints at a deeper debate about what probability even is. One view, the frequentist view, says probability is all about running an experiment over and over again. But the Bayesian view, which we're using, sees probability as a measure of our belief. And that makes it super powerful for one-off situations, right? You can't have 1,000 earthquakes to find the odds of the next one, but you can have a degree of belief based on the evidence you have. Okay, so we've got our final number, a 90% chance of a dog. But a probability isn't a decision, is it? So next up, how does a machine actually take that number and turn it into a concrete action, like stay or go? Well, what a machine does is create a decision boundary. It's like drawing a line in the sand. On one side of the line, the decision is dog. On the other, it's wolf. The machine uses a mathematical rule called a discriminant function to figure out exactly where that line should go. And it places that line right at the point of perfect indecision, where the scores for both dog and wolf are exactly equal. But just drawing a line at the 50-50 point isn't always smart, is it? Because, and this is so important, not all errors are equal. Mistaking a dog for a wolf? Well, that's a small mistake, no big deal. But mistaking a wolf for a dog? That could be, well, a disaster. We can actually put numbers on this with something called a loss function, which assigns a cost to every possible error. So let's imagine Lisa's internal calculation. Getting mushrooms is a small win, maybe a +1. But a run-in with a wolf, that's a huge negative, let's say -1,000. When the machine multiplies these costs by their probabilities, it gets the expected risk. And even with a 90% chance of it being a dog, that tiny chance of a catastrophic -1,000 makes going into the forest an incredibly risky choice. The math is clear. The safest decision is to stay home. Now, that whole process was for just one piece of evidence, the paw print. But what happens in the real world where you have lots of clues? The size, the depth, the time of day, the location. I mean, trying to calculate the combined probability of all that gets ridiculously complex really fast. This is where a clever little shortcut called the Naive Bayes Classifier comes in. It makes one big, simplifying, and technically naive assumption. It just pretends that all of these clues are independent of each other. Now, we know that's not perfectly true. Paw depth and size are obviously related. But this assumption lets us do something super simple. Just multiply their individual probabilities together. It turns an impossible calculation into basic math. And you know what? It works surprisingly well for things like spam filters, because even as the final number isn't perfect, the mountain of evidence usually points you in the right direction.
So we've built our machine, it's using priors, likelihoods, maybe a loss function, it's making decisions. But here's the final crucial question. How do we even know if it's any good?
We usually start with something called a confusion matrix. For any decision, there are only 4 possible outcomes. You have 2 where the machine got it right, true positives and true negatives, and 2 where it got it wrong, false positives and false negatives. This simple little grid is the absolute bedrock for measuring how well a model is performing. Now, from that matrix, we can draw a really useful graph called a receiver operating characteristic curve, or just ROC curve for short. What this shows you is a critical trade-off. The vertical axis shows your true positive rate. How good are you at finding the wolves when they're actually there? The horizontal axis shows the false positive rate. How often do you cry wolf when it's just a dog? A perfect model shoots straight up to that top left corner, 100% detection with 0 false alarms. And then we can take that entire curve and boil it down to a single number, the area under the curve, or AUC. An AUC of 0.5 means your model is no better than flipping a coin. An AUC of 1.0 means it's absolutely perfect. This gives us one simple, powerful score we can use to compare different models head-to-head. And that brings us to our final thought for the day. It's so easy to hear a score like 99% accuracy and think, wow, that's amazing. But you always have to ask, what's hiding in that other 1%? What if that tiny error is a missed cancer diagnosis or a self-driving car misjudging a pedestrian? It's a powerful reminder that behind all the numbers and all the curves, the most important question we can ask about any automated system is still the same. What's the real-world cost of getting it wrong?